Alright, let's continue talking about forming an acetal and the full mechanism behind it. First of all, this is the overall effect. You start with a carbonyl, like an aldehyde or ketone. You add in one equivalent of alcohol, any alcohol, in the presence of acid, and what happens is you form the hemiacetal. We'll see how the acid interacts with the carbonyl and how this alcohol, as a weak nucleophile, then attacks and forms this compound, the hemiacetal. If there's another equivalent of alcohol and even more acid to react with, the hemiacetal will progress to the full acetal. Instead of an OH and OR group bound to the hemiacetal carbon, now you have two OR groups at what's called the acetal carbon. And this OH group is protonated and then comes off as a water molecule. So throughout this entire mechanism, R' and R double prime, these variable groups bound to the carbonyl, are unaffected. The only thing that changes or reacts is this portion. Now what's the use? Well, here's one example. Installing the 1,3-dioxolane carbonyl protecting group. That's a handful to say. Basically, we can use this compound here. This is ethylene glycol. Now ethylene glycol has two OH groups and kind of functions like two different alcohols. You can consider this one equivalent, or 1 mole, even though it has 2 moles of OH. So what it can do is react with the carbonyl twice. Instead of having 2 equivalents or 2 moles in solution, we can just add in 1 equivalent of ethylene glycol, enough acetophenone to react with in the presence of acid, and we form this weird alien-looking structure called the 1,3-dioxolane. It's a protecting group. Now why is that important? Well, let's say you have this structure here, and this happens to be some R group. In other words, let's say you have a beta keto acid, where at the beta position you have a ketone, here's alpha, here's carbon 1. So, let's say the reaction of choice is to do this, to have the carbonyl still present at the beta position, but instead, at carbon 1, we'd like to do this. Instead of having the carboxylic acid, we want an OH group bound to carbon 1. Well, this is a reduction, where we're reducing the carboxylic acid all the way down to the alcohol. Well, what do? We need to preserve the carbonyl so that it's in our product, but we need to use some sort of strong enough reagent to reduce the carboxylic acid. This is where the protecting group comes in. We can add in ethylene glycol. Let's just write protect. So we can protect the carbonyl with ethylene glycol. We can then react the carboxylic acid with some reducing agent. And finally, we can remove the protecting group. Let's just write deprotect. This is one way you can affect one functional group but protect another using ethylene glycol. Okay? And to deprotect, we can use some acid, we can heat up the reaction mixture, and force the equilibrium in the reverse direction to remove ethylene glycol and regenerate the carbonyl. Okay? To install this protecting group, we need to form an acetal. Remember, R' here is our phenyl group. R double prime is the methyl. Our OR groups just so happen to be joined to one another because we're not using 2 equivalents of alcohol. We're using ethylene glycol. It has 2 moles of OH. Now before we go into the mechanism of this, let's quickly look at some other examples of acetals. Well, for one, without getting too much into carbohydrates and other units, let's just look at the structure of glucose, which looks a little like this. So in this structure, let's try to apply what we learned about hemiacetals and full acetals. Well, if you analyze all the carbons here, you'll eventually find this one right here. This carbon is the hemiacetal carbon, where towards the right we have an OH, and towards the left we have some OR group, okay? Some ether portion. But if we react alpha-D-glucopyranose, the cyclic form of glucose, with some equivalent of alcohol, let's say ethanol, we can form a full acetal. In the context of sugars, those are glycosides. Now, this is an acetal carbon. because it resembles this general structure here. And I should mention it's not alpha, but it's beta. So now let's dive into the mechanism. How do we go from a carbonyl to an acetal, such as this 1,3-dioxolane protecting group? Now, I like to use stupid human tricks to remember this, but don't rely on memorizing PAD and PED. Before I even explain this, just try to understand the logic of the mechanism. Why are we doing one step? Why it leads to the next? That's what we should be thinking about. Now, before we start, PAD refers to forming the hemiacetal, and PED refers to forming the full acetal. All P's refer to protonation, A's are addition, D's are deprotonation, E is this elimination of the leaving group. So PAD and then PED. That's one way to remember this. Now let's explain the logic here. We're starting with acetylphenone. We understand that forming the hemiacetal intermediate in the mechanism requires some acid and eventually some equivalent of alcohol. In this case, one equivalent of OH. So, to eventually add the alcohol, which is a weak nucleophile, first we need to protonate the carbonyl oxygen. Why is that? Well, when you do this protonation, the carbonyl oxygen acquires the proton from some general acid, H3O+, and we form water. The carbonyl oxygen is protonated and bears a full positive charge. But in its other resonance contributing structure, we can disperse this positive charge by moving this pair of electrons back to the oxygen, which gives the carbonyl carbon a positive charge as well. So we've dispersed the positive charge over two atoms. Why is this important? Well, it leads to the next step, which is the addition of the nucleophile. Here's ethylene glycol. Now it can more readily attack the carbonyl carbon because it's now even more electrophilic. So this protonation step increases the electrophilicity, which is an important concept. Both of these atoms are now even more positively charged, and upon attack from ethylene glycol, the pi bond breaks and we form this intermediate here. Now we're pretty close to forming the hemiacetal. Remember, it has an OH portion and some OR portion. It's logical then to carry out the deprotonation step. So that culminates the PAD part of this mechanism. Upon deprotonation, we form the hemiacetal. So let's remove this proton right here. And upon abstraction of this proton by water, we regenerate acid. So this mechanism is acid catalyzed. Now let's move on to the next phase. If we want to form the full acetal, we need to carry out PED. Protonation, elimination, addition, deprotonation. Let's make sense of this. Now we know we need to start with protonation of Lg, our leaving group. Now why is that? Well, this oxygen here can also take on the proton. That is why this entire mechanism is reversible. If this oxygen here acquires the proton again, we can then form ethylene glycol again. This becomes a good leaving group and can jump off the compound and reform ethylene glycol and our protonated carbonyl. We don't want that. We control the reaction conditions such that the proton more readily is put onto the OH. If we put the proton onto the OH group right here, we can carry out the elimination. Water happens to be a very good leaving group. So if we use the acid that's formed in step 3, bring that here, carry out the protonation, where this oxygen more readily takes on the proton. Not only do we form water here, but now we have a water molecule that's ready to leave the compound. Water is a good leaving group. So with this, let's carry out the elimination. The donation of electrons from this oxygen on the ethylene glycol portion will kick out the water molecule. So that's where this water is coming from. It's this loss of the leaving group. Okay, this is our leaving group. This oxygen can form a partial pi bond character right here and force out water as the leaving group. This also has a resonance contributing structure. The adjacent carbon can also bear the positive charge, and we could show that with this movement of electrons. If this electron pair goes back to oxygen here, we indicate that lone pair and a positive charge here. This is resonance stabilized. Now another thing to mention is that the carbons here and here are sp3 hybridized. There is free rotation. So this ethylene glycol portion can kind of bend on itself, which is why I drew it like this. That's going to be important for the next step. So we've done protonation, we've done elimination. All that's left is addition, number 2, and deprotonation. That will give us the full acetal. Let's see. We have this resonance stabilized structure, but we need to understand that we still have 2 lone pairs here that are ready to react. Think of this portion of the molecule as being partially negative, having some weak nucleophilic character. Well, this OH can come in and attack the carbonyl carbonate, and that's exactly what happens. In the case of ethylene glycol, remember, we theoretically have 1 mole of ethylene glycol, 1 equivalent, but we have 2 equivalents of OH, 2 moles of OH. One reacts to form the hemiacetal, the other reacts to form the full acetal. So this is what happens in the second last step, the second addition. Just like we said here, the OH attacks the carbonyl carbon. The pi bond breaks, and we form our alien-like structure with just an extra proton here. That's coming from here. So logically, let's remove that proton. Let's use one of these water molecules that we formed in steps 4 and 5. Let's bring that in for the last step. The water molecule comes in, plucks off the proton. This is our electron flow back to oxygen. And finally, we've protected the carbonyl. We've formed the 1,3-dioxolane. We've formed the alien structure. This is our protected carbonyl. And we've regenerated the acid. So again, this indicates acid catalysis. We've regenerated the catalyst. Now we have the full acetal.